So I guess this time also there's some other conferences going on, so that might explain the numbers of attendance maybe go up and down. Okay, so we have happy to have Junyi Xie. So yeah, from University of Rennes, right? Rennes, yeah, Rennes 1, and he will talk about visualization problems for degree sequences. Yeah, so please.
Okay, thank you very much for the organizer. And today I want to talk about the realization problem for degree sequence. Okay.
I remember in
here is the plan of the talk. At first, I will briefly introduce the dynamical degree and the degree sequence. And then I present a class of problem. We call it a realization problem. And we will introduce topology. We call it adelic topology. And this topology will be useful in realization problems. And then we present our result. And yeah, at the end, we give the proof of the main result. I forgot to say that this is joint work with serti Cantat and serti. Okay. Okay. So let K be an algebraically closed field of characteristic Z, and let F be a operational self-map. Be a operational self-map of Pn. So we may write F as Fz, F1 to Fn, where Fi are homogeneous polynomials of degree D without a common factor. Then the algebraic degree we write as degree 1F is just D. In other words, more geometrically, we may write degree 1F equal to F pullback H intersect H n-1 10, where H is the hyperplane of Pn. More generally, for every I equal to Z to N, we may define the ith algebraic degree to be degree IF equal to F pullback Hi times Hn-1. The ith degree sequence is just the sequence degree IFN for all n in Z. And the ith dynamical degree is defined to be lambda I, which is the limit degree I Fn 1 over n. And this limit converge. And this definition is made by many people. It's made by Husakovsky and Schiffman for Pn over a complex number, and then by Ding-Sibony for all complex projective variety, and then by Tong and by Dang for all variety over any field. Okay, and we denote by Ri Pnk to be the set of ith degree sequence for all operational self-map F of Pn over K, and lambda I gamma this and lambda I Pnk to be the set of dynamical the ith dynamical degree of operational self-map of Pnk. Okay, so general question is to describe Ri PNK and gamma I PNK. So I think this is a very general question, but it's important in algebraic dynamics. And in our talk, we mainly interest in the case when I equal to 1. So usually we just drop I when I equal to 1. For example, we write a degree for degree 1, Rpnk for R1 PNK. Okay, here is some known result for this question 1. I think we know quite many information in the surface case due to the work of Delafarge, Guizat-Toulon, Blanc-Cantat, and many people. For example, we can show that the growth of degree sequence for operational self-map of P2 is either bounded or linear or quadratic or exponential. And we also know that the dynamical degree is either it's always an algebraic integer, and in this case it's always an algebraic integer, and it is either 1 or a sudden number or a piso number. Okay. In high dimension, we know very few about these two sets. Here is some known result by Cantat and myself. We showed that for degree sequence, if it is unbounded if and only if it tends to infinity. And we also showed that for a degree sequence, if it is unbounded, then its growth cannot be too slow. I mean, too slow is cannot be slow than some very weak bound, something slower than log n, something like that. Okay, recently there is a breakthrough in this topic due to Delafarge. They showed that if lambda 1 square strictly larger than lambda 2, then degree Fn equal to C lambda 1n plus some O lambda n, where lambda is larger than lambda 2 1 over n and less than lambda 1. And recently also Longzhu and Yuhesh, they proved that if F is not pseudo regularizable, then degree Fn is at least linear. Okay, I will not give the definition of pseudo regularizable, but I think a general F is not pseudo regularizable. Okay, and so the question 1 is very hard question. So now maybe we want to consider some question relate to it, but easier. A priori, if we have a field extension k in k prime, then Ri PNK is contained in Ri PNK prime, and lambda I PNK is contained in lambda I PNK prime, because over a larger field you have more operational self-map. In particular, when k equal to q bar, it should be the minimal one. So Ri Pn Q bar should contained in Ri Pn K for every K. Also, lambda I Pn Q bar is contained in lambda I Pn K. Okay, so with Cantat and DZD, we ask the following question: do we have lambda I Pn Q bar equal to lambda I Pn K, or even Ri Pn Q bar equal to Ri Pn K for every algebraically closed field of characteristic Z? It just means that if you have some F, some Berational self-map F defined over some algebraically closed field of characteristic Z, then can we find another Berational self-map which is defined over Q bar, which has the same degree sequence? Okay. Maybe we can also ask a more precise version. Let B be a variety over K, and we say that a family FB B in B of Berational self-map of Pn is a Berational self-map F capital B Pn to Pn over this variety B, such that for every point B over the on the fiber at B, FB is birational. So it's just a family of birational self-map. We denote by eta B the generic point of B. So we may ask the question 3. For I equal to 1 to n minus 1, is there a k point B in this space B such that lambda I FB equal to lambda I F eta B, or even degree I F, the degree sequence degree I FBn equal to degree I F eta Bn for all n in Z. Okay. So maybe it just means that, for example, if you have a family of Berational self-map, then can you find a close point such that at this close point, the degree sequence of this Berational self-map equal to the degree sequence of the generic at the generic point. Okay. Here we have some remarks. If we have if question 3 has a positive answer, 1k equal to q bar, then question 2 has a positive answer. And it's clear that for every point B in B, the degree sequence of FBn of FB is less equal to the degree sequence at the generic point. Okay, and this question 3 is very easy. 1k is uncountable because for every n in Z, there is a non-empty open subset Un of B such that degree I F Bn equal to degree I F eta Bn for all B in Un. So if K is uncountable, then you take the intersection of all these UNK, this is non-empty. Okay, so this question 3 is can be viewed as an example of a class of question, and we call them realization problems. Here we present this class of problems. Let X be a variety over an algebraically closed field K. Let S be an algebraic structure on X. It can be an empty set, a rational self-map, or line bundle, or other things. Let PKXS be an algebraic property for points in XK, which depends on KX and S. Realization problems ask what's the minimal transcendence degree RP KXS of a field extension capital K of K, such that P capital K X K S K holds for at least one point X in XK if such K exists. Here X K S K are the base change of X S by K. In particular, in many cases, we ask is this transcendence degree equal to 0? Loosely speaking, we ask a property which generically holds can be realized for at least one algebraic point. Okay. In many cases, this problem only interesting when K is countable. Here we have some examples. The first example is a Zariski dense orbit conjecture, and this is quite it's an important conjecture in algebraic dynamics. It says that if K is an algebraically closed field of characteristic Z, X is an irreducible projective variety. F from X to X is a dominant rational self-map denoted by KXF, the field of F invariant rational functions. And then the Zariski dense orbit conjecture, it was proposed by Medvedev, Scanlon, Amerik, Bogomolov, Hoinsky, and by Zhang. If KXF equal to K means if there is no F invariant, if there is no non-constant F invariant function, then there is a K point X whose F orbit is well defined and is Zariski dense in X. Okay, so if we take the algebraic structure S to be this rational self-map F, and we take the property for K point X to be the F orbit of X is Zariski dense in X, then the Zariski dense orbit conjecture just asks whether RP equal to 0. So this makes this conjecture as a realization problem. Another example, if X is a non-unirooted variety, S is an empty set, and P is the property P for points in XK is X is not contained in a rational curve because X is non-unirational. So a very general point is not contained in a rational curve. But here we ask this X is contained in this space field K. So maybe, for example, when K is countable, that's the interesting case. We ask whether RP equal to 0. When K is Q bar or FP bar, and X is a non-unirooted K-shaped surface over K, this question was asked by Bogomolov in 1981. Okay, And example 3, here we let B equal to a variety over K. S is a family of rational self-map FB Pn to Pn. And the property P for a point B is degree I Fbn equal to degree I F eta Bn for every n in Z. Then if we ask whether Rp equal to 0, then we get our question straight. Okay, so for the realization problem, is something like if we have some property which holds for some kind of, for example, some very general point, can you find one point which satisfy this property? But sometimes we can ask some stronger question. We can ask whether almost all points satisfy this property. So to describe what does almost all mean, we may introduce new topology, and we call it the adelic topology.
Can I ask a question?
Okay.
So in your previous slide, you mentioned the RP is 0 is equivalent to your question 3. Can you explain a little bit about why they are the same? I don't understand this RP is 0. What does that mean?
RP equal to 0 means that you don't need to take a base change, because K is an algebraically closed field. So so RP means what? RP is the minimal transcendence degree you need to base change to get a K point, to get a closed point, which satisfy the property. The property. And equal to 0 means that you don't need to take base change. Okay.
Yes, yes, yeah.
Okay. So now we assume that the transcendence degree of K over Q bar is less to is finite. Okay, let X be a not necessarily irreducible variety over K. In a previous work, I introduced a new nature topology on XK and call it the adelic topology. The definition is as follows. We first pick a subfield KZ of K such that KZ is finitely generated over Q. Its algebraic closure equal to K, and X is defined over KZ. It means that there is a variety X KZ over KZ such that X is just the base change of X KZ by K. We fix this subfield, but we will show in the end that the adelic topology does not depend on the choice of this base field KZ. Okay, let K be any finite extension of KZ. Set XK to be the base change by K of X KZ. We denote by IK the set of field embedding tau from K to CP tau, where P tau is either prime or infinite. Here, C infinite is just a C, the field of complex number. For every tau in IK, we denote by I tau the set of field extension tau bar from K to CP tau, which extends the given field embedding tau. Okay. For every tau bar in I tau, it induces an embedding phi tau bar from xk to x k cp tau, and on x k cp tau we have the p tau adic topology, and when p tau equal to infinite, this is just the topology of complex manifold. Okay. Okay. So for every embedding tau in IK and every p tau adic open subset U in X CP tau, we denote by X K tau U the union of tau bar in I tau phi tau bar minus 1 U in XK. This is, how can we say? This is just a subset of XK such that there is an extension of the field embedding tau, which sends this point in the given open subset U. And this subset is called the adelic subset associated to U and tau. We denote by basic adelic subset over over this field K to be xk tau I from 1 to m, which is the intersection of the adelic subset associated to ui and tau I. Okay, and basic adelic subset is just basic adelic subset over some k. Here k is some finite extension of kz. Then we define a general adelic subset to be image of a basic adelic subset by a flat morphism. Okay, now we can define the adelic topology. We define adelic open subset to be a union of general adelic subsets, and they form the adelic topology. And general adelic subsets forms a base for this topology. The adelic topology does not depend on the choice of the base field kz. Okay. I think I want to explain why we consider this subset xk tau u, the adelic subset associated to tau and u, because if S is an algebraic structure on X, for example, a rational self-map F, which is defined over K, and let P be an algebraic property for points of X, which depends on S. For example, the Zariski closure of OFX is irreducible. This is a property, it's purely algebraic. Okay, and if this property P satisfies for all points in the P tau adic or complex open subset U in X CP tau, then because our property P is purely algebraic, so it does not depend on which field embedding you choose. So P is satisfied for all points in the adelic open subset X K tau U. That's why we want to consider this subset. Okay, here we list some basic properties of the adelic topology. First, it is stronger than the Zariski topology, and it is T1, means that for every distinct points xy in xk, there is an adelic open subset U of xk, which contains x but not y. Morphisms between algebraic variety over k are continuous. Flat morphisms are open. Let k be any subfield of k, which is finitely generated over q, and such that x is defined over k, k bar equal to k. Then the action of the Galois group, k over capital K on xk, is continuous. And the last one, the irreducible components of xk in the Zariski topology are exactly the irreducible components of xk in the adelic topology. So I think all these properties are satisfied for the Zariski topology. So maybe we can think adelic topology is something quite similar to the Zariski topology, but it is stronger. And the properties 1 to 5 are not so difficult. And I think for our application, the last one is the most important one. For example, if x is irreducible, then the last property, property 6, it implies that the intersection of finitely many non-empty adelic open subsets of x is still non-empty. When dimension x large equal to 1, then the adelic topology is not Hausdorff, and it is strictly stronger than the Zariski topology. Here is an example. Let k equal to q bar, and x is the affine line. Tau is the unique unbending from tau from q to c. We denote by u1 the open unidisk, and u2 to be the set of x in C with norm strictly larger than 1. Okay, then the set 1 over 2, 1 over 3, 1 over 4, blah blah blah. This is contained in A1Q tau U1, but not in A1Q tau U2. And the set 2, 3, 4, blah blah blah. This is contained in A1Q tau U2, but not in A1 tau A1Q tau U1. Okay, and the set n plus or minus 1 over n square minus 1 1 over 2 for n large equal to 2. This is an infinite set. It is contained in the intersection of the adelic subset associated to U1 and to U2. So we note that even here, the intersection of U1 and U2 is empty, but the intersection of the adelic subset associated to them are not empty. So as we said before, a realization problem asks one point in xk satisfy some property, and it can be straightened to ask almost all points in xk satisfy some property. Usually we have two notions to speak of almost all points in xk. One is general, another is very general. We say that some property is satisfied for a general point means there is a non-empty Zariski open subset such that all points in this subset satisfy this property. And we say that this property satisfied for a very general point means that outside a countable union of proper subvarieties, this all points satisfy this property. But for our problem, usually the notion general is too strong for realization problems, and because we mainly interest in the case when k is countable. In this case, there is no very general point. So using adelic topology, we get a third notion to speak of almost all points in xk. Assume x is irreducible. We see that a property P holds for an adelic general point if there is a non-empty adelic open subset U of xk such that P holds for all points in U. So how can we use this notion? If there are two properties P and Q, and if both P and Q hold for an adelic general point, then an adelic general point satisfy those properties P and Q in the same time. So this gives us a way to split a problem to some easier problem. Okay, now we want to present our results concerning question 2 and 3. We first have the first result is as follows. Let F be Pn to Pn being B be a family of rational self-maps, and assume that the degree sequence at the generic point degree Fn eta B n in Z is bounded. Then for an adelic general B in Bk, the degree sequence of F eta B and the degree sequence of Fb are the same. So question 3 has a positive answer when the degree sequence at the generic point is bounded. So if we set Rb Pnk to be the set of bounded degree sequence for rational self-maps F of Pn divided over K. This is a subset of Rpnk. Okay, and then theorem 1 implies the following corollary: Rb Pnq bar equal to Rb Pnk for every algebraically closed field K of characteristic Z. So it means that if you have any degree sequence over some algebraically closed field of characteristic Z, for example, over C, if this degree sequence is bounded, then you can find another rational self-map over Q bar, which has the same degree sequence. Another corollary is as follows. So for every finite sequence A1 to AM of integer in Z, there is a natural number D and a rational self-map F of P2 divided over Q bar such that degree Fn equal to 1 when n equal to 0, d plus an when the absolute value of n is larger than 1 less equal to m, and for the other n, when its absolute value large equal to m, it's just a d. In other words, the degree sequence looks like this, and it is contained in RB P2 Q bar. Okay, so here we see that this degree sequence is it has some symmetry. For example, for example, an equal to a minus n and az equal to 1. But here, in fact, for all an in RP2K, we have this property. And we also show that this D is necessary because we have the following result. I proved that if F is a rational self-mapper of P2, and if degree F2 strictly larger than 318 2 1/2 degree F, then lambda 1F is strictly larger than 1, so it cannot be bounded. So if we have a sequence whose first term is 1, A2 is 2, and A3 is 3, 19 times 4, then this sequence cannot be contained in RB P2 Q bar. Okay, the idea of the proof is first we construct such sequence in RB P2C. Here we do the things over C, then you get some freedom. You can choose some element in some very general element in some family, and then we apply our corollary 1 to get this F over Q bar. Okay, and another result, theorem 2, let F from Pn to Pn be a rational self-mapper of degree D large equal to 1. Here we consider a special family, A home F from Pn to Pn, where A is in PGL n-1. Then for an adelic general element AZ in PGL n+1 K, we can show that the degree sequence of AZ home F is just Dn for every n in Z. In particular, lambda 1 AZ home F equal to D. And this theorem has the following application. Rational self-map G from Pn to Pn is called regularizable if there exists a projective variety X and a rational map phi from X to Pn such that phi minus 1G phi from X to X is an automorphism. It just means that you can conjugate your operational self-map to an automorphism on some projective variety. Because here we are in characteristic Z, we have some functional desingularization. So we can assume that X is smooth. Okay, and there is a question of Dologachev. Is there a operational self-map F from Pn to Pn with degree F large equal to 2, such that for every A in PGL n plus 1k, A home F is regularizable. And our theorem 2 implies that there's no such F. Okay, here is the proof why theorem 2 implies corollary 3. By theorem 2, there is A in PGL n plus 1k such that lambda 1 A home F equal to degree F large equal to 2, which is an integer. We claim that for any automorphism G from X to X of a smooth projective variety, lambda 1G is not contained in Z minus 1. The reason is that the lambda 1G plus minus 1 is an eigenvalue of G plus minus 1 X on the Nihon self-heat group N1X. So lambda 1 G plus minus 1 are algebraic integer. So if lambda 1 G is an integer large equal to 2, then lambda 1 G minus 1 cannot be an algebraic integer. Okay, so because lambda 1 is invariant on the operational conjugacy, so A home F is not regularizable. Okay. Okay, now we want to prove our theorem 1. Here is the proof. First, we apply Weiss regularization theorem to the rational self-map at the generic point F eta B. Then there is a smooth projective variety X eta B over KB, and operational map phi eta B from X eta B to the projective space Pn. Here is just a operational map. It may not be a morphism Pn KB, such that the induced map F eta B, capital F, phi eta B minus 1 F eta B phi eta B from X eta B to X eta B is an automorphism. So now after shrinking B, after shrinking the base, we may assume that there is a smooth B skin pi XB to B, and operational map phi B XB to PNB over B, and an automorphism FB on XB, such that their generic fiber X eta B, phi eta B, F eta B are the generic fibers of okay, such that these things are the generic fibers of XB, phi B, FB. In particular, FB equal to phi B minus 1 Hong FB Hong phi B. Okay, now we denote by alt BXB the automorphism group scheme of XB over B. So it is every connected component of this group scheme is of finite type, but it may have infinitely many connected components. And our automorphism FB can be viewed as a section of alt B XB. Okay, and for every point B in B, alt XB is the fiber of this group scheme, alt capital B X capital B at this point B, and the specialization FB of F capital B is in alt XB, and for every G in alt XB, it induced a bidirectional map on Pn by phi B Hong phi B minus 1. Okay, now we denote by GB the Zariski closure of capital F eta Bn n in Z in alt BXB. Because we know that this F eta B is of bounded degree. So this GB is of finite type. So the GB to B is a group scheme over B of finite type. Okay. Now this FB, we can view this FB as a B point in GB, and then it defines an automorphism of GB L by left translation by FB. More precisely, for every point G in some fiber GB, L X on G is just FB Hong G in GB. Now we consider a function from this from GB to non-negative integer by for every point G in GB, it induces a bidirectional self-map on Pn by phi B Hong G Hong phi B minus 1. Then we take the degree. It's easy to show that this function delta from GB to Z large equal to Z is lower semi-continuous with respect to the Zariski topology. So it is continuous with respect to the constructible topology. Okay, the constructible topology is the topology on GB generated by all constructible subsets. Now we view GB as a K variety, so not a B scheme, but a K variety. Then we set Z to be the image of this section FB in GB. So it is a subvariety of GB, whose generic point is just F eta B. So we only need to show the following statement for every for an adelic general point X in zk. Delta lnx equal to delta ln f eta b for every n. Okay, now we just conclude the proof by the following theorem. Theorem 3. Let f x to x be an automorphism of a variety over k. Let chi from x to z be a function which is continuous with respect to the constructible topology. Let z in X be an irreducible subvariety with generic point eta. Then for an adelic general X in ZK, eta chi fnx equal to chi fn eta for every n in Z. Thank you. Okay.
Yeah, thank you, Junyi, for very interesting talk. Any questions?
Yeah, so I have a question about your adelic topology on this variety. So can you generalize this adelic topology to schemes? For example, to like a spec OK of for number fields.
I don't know because I think the adelic topology is for example here we only care about the k point, the close point. We don't care about the other scheme theoretic point. So I think for example, in characteristic positive, in positive characteristic, I think we can have some analog of this topology. So if you want just a direct analog for scheme, I think you can just do it for the close points. So this should be okay, but I think maybe it's not so interesting. So I don't know, because I think the point is here we only care about the close point, not the other scheme theoretic point. That's the point of the adelic topology. So.
All right. Okay.
Okay, so I have some questions. So in first of all, in this theorem 3, do you need F to be an automorphism, or you only need first of all a morphism? Is this enough, or do you need
excuse me, because I cannot hear very clear what you said.
Yeah, so my question is that for example in theorem 3, you assume that F is an automorphism, and then you prove this equality at the end.
Okay. The last.
Then the question is, if you don't have an automorphism, but maybe you have a morphism, then can you still prove it, or you need automorphism to be able to do it?
I think one point is that here we wanted the sequence the index by z. So that's why we ask it to be an automorphism. And if we only consider forward orbit, I think I think we only need the x to be unramified. So if we assume that F is unramified and we only consider the forward orbit, then I think the proof is almost the same. But I think our method does not work in general because we used some periodic parameterization lemma, and for apply this, I think there is always some trouble if F is ramified.
Okay, I see. Then second question is that here f x to x say an automorphism, then you prove that f is continuous with respect to the idealic topology. So then maybe you can consider entropy and are they the same or you don't know?
Can you say it again? The entropy of what?
Of this map F as automorphism of a variety, okay, and of this F as a continuous function on the idealic topology.
You mean for idealic topology computed the entropy of automorphism, right?
Yeah, so are they the same?
I think that this is strange. I don't know because for me the idealic topology I don't use it as a topology. I use it as a language to speak of almost all points. So because I think a variety on the idealic topology maybe it's not quasi-compact, I think. So so I don't know. I'm not so sure whether it is interesting to think idealic topology as a topology. I think it's interesting to think idealic topology as some kind of some notion of almost all points, or something like that.
Okay, I see. Okay.
So this notion almost all point is weaker than the Zariski topology. Is that right?
It's weak, yes, because this topology is stronger than Zariski topology. So this notion as almost all point is weaker.
Okay.
Okay. Yeah. Thank you. Any other questions? Yeah, if not, then yeah, take Junyi again and
okay.
when is the next?